Day 4 of notes, stoichiometry, still with the cool word. We're going to talk about limiting reactants. And that's exactly what it means. It's a reactant that limits how much product you can make. It's a limiting reactant. And what we're going to do is decide which reactant runs out first. So let's read here. The limiting reactant, LR for short, is the reactant which runs out first. And that limits the amount of product that can be made. So in layman's terms, the reactant that will run out and there will be no more production after that reactant runs out. Meaning you can have excess of another reactant or multiple reactants, but when one of those reactants run out, you no longer have the ingredients to make more product. So the chemical reaction will stop. And how do we solve those? Well, we're going to be using two mass-to-mass calculations, meaning we're going to get the mass of one reactant and convert it to moles of that reactant, and then moles of that reactant to the product of that chemical reaction, and then that mole of that product will be converted to mass. So we're going mass or grams to moles, moles to moles, moles to grams, which is nothing new. We've done that on day 2 of these notes. We're just deciding which is a limiting reactant now. And of course, like I've already said, the limiting reactant is the one that produces the smaller amount. So let's look at an everyday example. We're going to make some funfetti cupcakes. So in order to make a cupcake or a pan of cupcakes, we need one mix. We need 3 eggs. We need 2 teaspoons of oil to get one pan of cupcakes. We have to have 1 mix, 3 eggs, and 2 oils. Pretend these are chemical reactants. We're just calling them a mix, eggs, and oil for every 1 pan of cupcakes that's being produced. And by the way, cooking is chemistry. And if you want to get better in cooking, you need to have a better understanding of chemistry. Anyway, so let's say that in my pantry, I actually have 3 bags of mix. I have 15 eggs available, and I have 8 teaspoons of oil. That's all I have. That's it. I don't have any more unless I go to Walmart and steal someone's lunch money. So let's convert each one of these reactants to our product, which is the pan of cupcakes. So we're going to use dimensional analysis. So I know for every 1 mix, I can produce 1 pan of cupcakes. So let's put that up here. For every 1 mix, cake mix, I get a pan of cupcakes. Multiply across, I can produce 3 pans of cupcakes with 3 mixes. All right, let's do the same thing for eggs. I know that for every 3 eggs, I have 1 pan of cupcakes. So multiply across and then divide, out of 15 eggs that I have, and that's all I have, I can produce 5 pans of cupcakes. Now with 8 teaspoons of oil, I know that for every 2 teaspoons of oil, I can produce 1 pan of cupcakes. So teaspoon of oil goes on the bottom, so it cancels out for every 1 pan of cupcake, and I get 4 pans. Notice how I'm using dimensional analysis with ingredients. We do the same thing with chemicals, with moles, with molecules. There is no difference. Dimensional analysis can be used everywhere, and we use it every day without even realizing it. So out of all of my product, I made 3 pans of cupcakes, 5 pans of cupcakes, and 4 pans of cupcakes. But actually, with my ingredients that I have, and I only have those, I can't magically produce more unless I go to Walmart or steal someone's lunch money to go buy more. I could only make 3 pans. Right here, 3. Why? Because the mixes are limiting how many pans of cupcakes I can make because they're used up first. Once I use up my 3 mixes, it doesn't matter if I have excess eggs and excess teaspoons of oil. I have to have all 3 mixes, eggs, and oil to make a pan of cupcakes. But if I run out of the cupcake mix, I can't produce any more cupcakes. It's just impossible. It won't happen. It won't exist. So we say that the mixes are limiting. They are the limiting reactant in this chemical equation or in this cooking equation. So let's apply it to chemistry. If 17.1 grams of potassium reacts with 14.3 grams of fluorine, which reactant is the limiting reactant, and what mass of potassium fluoride can theoretically be produced? So let's first write the chemical equation. Potassium is going to react with fluorine, and using my Unit 9 rules, I know that I'm going to produce potassium fluoride. Let's do a balanced chemical equation. I have 2 moles of potassium, 1 mole of fluorine, and 2 moles of potassium fluoride in a balanced equation. I'm given 17.1 grams of my potassium because that's how much I had in my closet. That's how much I had in my pantry. I'm given 14.3 grams of fluorine because that's what I had available in my pantry. So how much product, potassium fluoride, can I produce? How much pans of cupcakes can I produce? So I'm going to have to convert my grams of potassium to grams of product, potassium fluoride. So start with what you're given, 17.1 grams of potassium. I convert my grams of potassium to moles of potassium because I use my periodic table. For every 1 mole of potassium, there's 39.1 grams of it, straight off of your periodic table. Now I need to convert moles of potassium to moles of my product, because that's really what I'm looking for. So using mole-to-mole ratios, 2 moles of potassium for every 2 moles of potassium fluoride. And my moles of potassium will cancel out. Now I need grams of potassium fluoride because that's actually what I'm producing. How many grams? I need to know. And that's what I'm asking in the question, what mass of potassium fluoride? So I'm going to have to convert moles of potassium fluoride, use your periodic table. 39.1 plus 19 will give you 58.1. So moles of potassium fluoride goes on the bottom, giving me 58.1 grams of potassium fluoride. My moles cancel out. Now I plug and chug in my calculator and I come up with 25.4 grams of potassium fluoride. I still don't know which reactant, potassium or fluorine, is limiting. I don't know which one's smaller. So I need to figure out using fluorine now. So if I have 14.3 grams of fluorine available in my pantry to make some cupcakes, I need to convert those to cupcakes. So let's see how much I could theoretically produce. Theoretically means I'm actually using math to figure this out. So 14.3 grams of fluorine. I need to cancel those out using the periodic table. There's 38 grams of fluorine, F2. It's diatomic, so you have to say 19 times 2 for every 1 mole of fluorine. Those cancel out. For every 1 mole of fluorine, there is 2 moles of potassium fluoride. So 1 mole of fluorine for every 2 moles of potassium fluoride, because I need to get to my product. That's why I'm using the mole-to-mole ratio. Now, I need to know how much of my product I produced. So I need to convert my moles of my product to my grams of my product. The moles will cancel out because I know I have, for every 1 mole of potassium fluoride, I have 58.1 grams of potassium fluoride. That's my product. That's my grams. Plug and chug, I get 43.7 grams of potassium fluoride. So out of these 2 reactants, which one produced the least amount of product? It would be my potassium produced the least amount of product. So this is my limiting reactant. Potassium is my limiting reactant. I can only produce 25.4 grams of potassium fluoride if I had 17.1 grams of potassium available and 14.3 grams of fluorine. Why? Because it would my chemical reaction would stop once I ran out of potassium. Even though I have excess fluorine, my chemical reaction will stop due to my limiting reactant, which is potassium. Notice how I actually had less fluorine here, but it produced more. So it's not about how much you have of something. You actually have to convert it into the product, doing mass to mole, mole to mass conversions to figure out how much product you will actually produce. So like I said, potassium is the limiting reactant, and 25.4 grams of potassium fluoride, our product, our cupcakes, can be produced. Let's go ahead and start the worksheet.